You're third year, right?
Yes.
All right, I would like to call this meeting to order, please. Thank you. How's everybody doing today? How about that weather, eh? Yeah.
So nice.
It is beautiful. It is delicious. It is delicious out today. My God. And it's been a hard winter, too, so I feel like we've earned it. So, we're going to finish off stepper motors today. We don't have too much left to cover yet. Basically, we just have to talk about power supply and how one isolates this from frying your motor. And after that, we're going to get into operational amplifiers. We're going to give those a somewhat thorough treatment. Did they do op amps with you guys previously? No. Not even a little bit? Okay. All right. Good. Awesome. Because I kind of prepared assuming you guys knew nothing, so that's good. You know, it seems like that's a pretty good assumption with a lot of these topics, is that you've never heard what I'm talking about before. So, you know, we'll make do. Anyway, so let's get into it, then, shall we? So last time, we had talked about the 6-pole stepper motor, how that is, you know, fundamentally very similar to having a 2-pole stepper motor. We also talked about the switched reluctance stepper motor, which required us to know what reluctance was. So we talked about that. And now all we have to talk about is how one goes about isolating these things. So, motors typically require more current than a typical microprocessor can supply. Depending on the size of the application, this might be the understatement of all understatements. Like, if you think in terms of like industrial control, some of the motors inside of plants can get quite phenomenally large and draw phenomenal amounts of power. So, control signals from a microprocessor are connected to a driver circuit. So, you drive motors with a motor driver. I know that sounds tautological, but that's the name of the component. If you want to supply power to a motor, you need to get a motor driver. That's sort of like if you, again, in an industrial setting, they have like these boxes that you can buy and insert into control panels called motor drivers that drive motors. Output from the driver circuit is connected to the motor. For a bipolar motor, we need to be able to reverse the current through the windings of the motor. So if the motor only spins in one direction, obviously you don't need as complicated circuitry. But if the motor can reverse direction, you need slightly more complicated machinery or circuitry. So this can be done using suitable switches. The electronic equivalent of such switches is called an H-bridge. It has forward and reverse modes. So this is what an H-bridge looks like. Supply at the top, ground at the bottom. Points A, B, C, and D here are the pickoff points that will be then sent out to the motor itself, right? That goes off to the motor. What's this guy? What's this symbol? Diode. What's this?
Inductor.
Inductor. Good. So there you go. Or wait, maybe I think I've got that reversed. I'm sorry, yeah, no, this is the controller. This inductor will be the coil of the actual motor. Yeah, sorry, I apologize for that. I had my wires crossed. So, incoming control signals, these will be the switches, A, B, C, and D. The coil that drives the motor is an inductor, right? So it's represented as an inductor even though it's part of a motor, right? These circuits are abstractions of physical reality. The part on the page does not necessarily resemble the part in reality. So we can switch, if we want the supply coming in on one side of the inductor, we can open switch A and open switch B. So you have current flowing thusly through the circuit. If you want to reverse the direction, close A and D, open B and C. Supply will run through, in this manner, down there. Make sense? Anybody have any idea what the purpose of these diodes is? Anybody want to take a wild guess? Yeah.
For the reverse current when the inductor powers down.
Yes, for the reverse current when the inductor is powered off. So, to what extent have you guys studied inductors? Like a little bit, a lot? Crickets? Crickets?
A little bit.
A little bit? Okay.
Like we've studied them within circuits and resistance and stuff, and impedance, but
Yeah, okay.
yeah.
So just a quick reminder then, with respect to the physical properties of inductors, right? So inductors take some time to build up their full magnetic magnetism, the full amount of magnetic flux flowing through them, right? So, like if you have an inductor, right, which shall be represented thusly, right? When you power this thing on, the flow is very slow to start, but as the current, as time goes on, the current will increase and eventually reach. It'll eventually reach your maximum. So these things, you sort of model them as having high resistance at first, which reduces over time as as time progresses and the same amount of voltage is applied to it, right? So, resistance decreases over time. Therefore, the voltage drop across them also decreases over time, and the current through them will increase over time because it's an inverse relationship. So, when you switch the thing off, it doesn't turn off immediately, right? So we all know, hopefully, that a magnetic flux, which is flowing through a coil, will induce current in that coil, right? So when you switch this off electrically, for a brief amount of time, the magnetic flux, which has been generated inside of this inductor, that's not switched off when you switch off the electricity. Magnetic flux doesn't act like that. It can't just be turned off instantaneously, right? So what happens is this magnetic flux will continue to induce current in the inductor even though the power is off. Like there's no longer voltage being applied to it, right? So there's no longer current flowing through it. So this has the effect, essentially, of dragging the electrons through the inductor or propelling them through the inductor even though there's no external source of power for them. This can result in very strange effects, right? Like, if you have, say you've got a switch that switches between, plus 5 volts and ground, right? And you're running this guy and then, running it through to ground here. right? If you were to measure the voltage across this over time, right? If we suddenly switch to the ground position, cutting off the electrical supply, the current is still going to continue to flow this way, right? Which will have the effect of, essentially you get a negative voltage across the thing while it's doing this, right? That voltage spike caused by the inductor can actually damage your electronics. So, what a diode does is allows electron flow in one direction but not the other, right? So, it is blocked on the direction that has the line and allowed with the direction of the arrow, right? So, if you have a buildup of charge on the ground on this line here, or even on this line, it's going to allow it to pass through to the other side, right? So, thus neutralizing that effect and protecting the circuit. Make sense? You guys with me? Any questions? Good. All right. So far, so good. So, switching on and off, switching phases on and off causes spikes in voltage. The above protects against switch spiking. If a cheaper but slower diode is used, a capacitor should be placed in parallel. Capacitors can have a similar effect, but you know, you can also just use good diodes. Good. Anyway, that's everything we have to say about stepper motors. Do we have any questions about stepper motors before we move on to our next topic? Boy. Loving the enthusiasm, guys. So, good. So, op amps. So we've kind of touched on the idea of operational amplifiers already. We've certainly talked about comparators, which are built from differential amplifiers. So it's about time we talked about what these blasted things do, right? Amplification is an absolutely necessary signal conditioning process for many different types of sensors or actuators, right? So, take for example, something like a strain measuring device, which is what, where are those guys who were working on the Wii balance board? Where are you guys? Up in the back there we go. So, the weight sensors in the corners of the Wii balance board, right? As you guys found out, the amount of voltage that they actually output is minuscule in comparison to what you can read with an analog to digital converter, right? In order to usefully read that signal, it needs to be amplified out of the millivolts range, right? And into something that's more reasonable. So operational amplifiers are one way to accomplish that goal, right? From a sort of, oh no, I've got a hair in my mouth. Oh no. Oh dear. And now I've got chalk in my mouth. Lovely. Anyway, so from the perspective of like overall circuit analysis, Operational amplifiers are often what is meant by current or voltage sources. Not exactly, but that's sort of in the ballpark, right? So, let's talk about, let's set this up with the idea of matching impedances. So, consider this circuit. Voltage source, some resistor, and a load resistor, right? VO being the voltage across the load resistor. Question. We want to power the load RL. Given RS, the output resistance of the DC voltage source, and the output resistance, and the DC voltage source Vs, what should the value of RL be to maximize the power absorbed by the load? Yes?
They have to be equal, right?
They do have to be equal, but did you know that you have to do calculus to figure that out? So, how do we understand how to maximize power here? Like, what's the process? Well, number one, we need to calculate the power, right? What's the formula for power?
I squared R.
I squared R. P is equal to I squared R. Okay, yep. So, R in this case being RL, right? So, it's a maximization problem. So what we actually want to do is we want to see the inflection point of the curve if you're taking power as a function of the resistance, right? The inflection point of that curve will be the point at which the slope is 0. So we take the derivative of power with respect to the resistance of the load, set that equal to 0, and see what we get. Right? Does that make sense? Little bit of calculus? So, so I've actually got the whole thing written out. Where's my little notebook? There we go. So, the voltage across the load, VL, which is also known as V out here, but, you know, is equal to the current multiplied by RL. There's only one loop here, so we only have one current to worry about. This I is equal to V over R, which is equal to Vs over RL plus Rs. Because the whole resistance of I'm going to put the circuit back up. The resistance of the entire circuit is, of course, the sum of these two resistors who are in series. Right? So, VL, therefore, is equal to RL times Vs over RL plus Rs. Yeah? So the power, as your esteemed colleague stated, VL squared over RL, which is equal to Vs times RL squared over RL times RL plus Rs, also squared. Right? You take this, plug it in, square it, You still have that, right? Good. So, we can, of course, break this apart so that, cross out that term. So, this is an expression for P in terms of RL with RS as a constant and VS as a constant. So, if we want to do dP by dRL, what rule are we using? Quotient rule. Yes, thank you. So, just as a reminder, quotient rule, d dx f over g is equal to f prime g minus g prime f over g squared. So in this case, what's f? F is equal to Vs squared RL. F prime? Yeah?
Vs squared.
Yep. Now we take G. G is the bottom bit, so RL plus RS squared. What's G prime?
Yeah, 2 times bracket RL plus RS.
2 times RL plus RS. So this guy is Vs squared times RL plus RS squared minus G, of course it's G, RL plus RS squared times Vs squared RL, there we go, over RL plus RS to the power of 4. Did I miss something?
G needs to be a good derivative.
G needs to be the
When you subtract, it's just, yeah.
Oh, yeah, sorry, pardon me. Thank you.
You also forgot the 2.
I forgot the 2. There. What else did I mess up? Let's see. F is this guy, which is here. G prime, there. Yes. Good, 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 good. We're good? Good. So, so perhaps we can spare ourselves the pain of expanding out those terms and collecting like terms. Jump ahead in the derivation just a little bit to this point, because, you know, the rest is algebra, which is beneath our level at this point, right? So, eventually, Vs squared times Rs squared minus RL squared over RL plus RS to the power of 4, right? So we set that equal to 0, right? So, if we take this, right, pop this over here, well, first of all, we can eliminate any constant terms. There we go. So, RL plus RS to the power of 4 is equal to RS squared minus RL squared. Oh wait, no, you can multiply that out as well. Pardon me, sorry. Yeah, what am I thinking? Geez, 0 is equal to that, which means that RS squared is equal to RL squared, which means RS is equal to RL. Good. So there you go. So, good. So if we want to maximize the amount of power that's in the load, we need to be able to match impedances with whatever resistance is being given out by the voltage source, right? So how do we do that? Operational amplifiers, of course. So, signal conditioning circuitry should have a large input impedance compared to the output impedance of the sensor transducer to reduce loading effects. So, essentially, you don't want, like when you're amplifying a signal, you don't want the thing doing the amplifying to behave in a, you don't want it contributing to the circuit very much, right? A little bit is unavoidable, but you want it to have a high impedance relative to the thing that it's amplifying, or so that it can be measured, right? So some sensors, such as piezoelectric sensors, have very high output impedance. Output signal levels are very low. Does anybody know what a piezoelectric device is? Yes?
It's something that makes noise when you put electricity through it.
It's something that makes noise when you put electricity through it. That is true. That is a functional description, but do you know what the thing actually is?
No.
No. Okay. Anybody? Anybody? Okay. So, piezoelectric devices are crystals whose shape morphs slightly when under pressure, or no, sorry. It runs two ways. By running an electric current through a piezoelectric crystal, it modifies its own shape slightly. Like it, you can if you have like a piezoelectric crystal, right, and you apply a voltage to it, let's put that off to the side, there. It will grow slightly larger. It will kind of compress up and like expand a little bit, right? And then when it decreases, when the voltage ends across it, it resumes its previous shape. And the degree to which this thing deforms is proportional to the voltage which is applied to it. So, okay, so big deal. You have a crystal that can squeeze and fatten according to how much voltage is applied to it. Practical applications. What is sound?
Waves.
Waves as transmitted through air, right? Or water, whichever. So, if you put a plate on the end of this thing, right? And like sort of put it inside of a thing that amplifies the waves that it generates, this is how a speaker works, right? A tiny crystal, which is sort of jumping up and down a little bit according to the voltage, right? That oscillation is transferred to the air. That air, the waves in the air are amplified by, all of the surrounding speaker bells and that sort of thing, directionalized and amplified. And that's how a speaker works, essentially, using piezoelectric crystals. You can also get a piezoelectric, you can have them do the same thing but in reverse, which is kind of fun. So this thing around my neck, which amplifies my voice, is a tiny piezoelectric crystal which is running, basically hooked up the other way around. If you depress this thing, it emits a small amount of voltage, right? Very small amount of voltage. So that's essentially what happens with a microphone. My voice, the sound waves hit the thing, cause very slight depressions in it, which are picked up as electricity and then amplified, right? So that's how piezoelectrics work. Anyway, these things tend to have reasonably high impedance. So in order to amplify them, we need something with even higher impedance. So impedance matching amplifiers have very high input impedance, very low output impedance, and unity gain. So essentially, the problem with just feeding something like this directly into your microcontroller, you can't actually force enough electrons through this device. Basically, you can think of it in terms of slew rate, right? You guys remember slew rate? They have a low enough slew rate that, like, you can't really power the type of machinery that's necessary in order to do analog to digital conversion on the signal. So you need an amplifier which gives you the same voltage back again, so it's a unity amplifier, right? However, the voltage which is flowing through the amplifier is backed up by much more possible current. So the electrons are provided with much less restriction, so you can actually do stuff with the signal. So let's talk about operational amplifiers. The symbol for an operational amplifier pretty universally is a triangle with a plus on one side and a minus on the other, two leads coming out like this, and a lead coming out there. In a circuit diagram, when you see this, this is an operational amplifier, right? The amplifier itself has an external power supply, external to these three leads, which are usually the only ones you're concerned about. So those are drawn from the top and bottom. Typically, they're omitted. You don't usually see them when you see a circuit diagram because it's just kind of assumed. Yes, of course, the amplifier needs a connection to, the positive and the negative voltage. Interestingly, on these, you can actually provide, you can feed actual negative voltage into these, and it'll still work. Like normally, we talk in the range of 0 to 5 volts, roughly speaking, but these things can invert signals into negative voltages as well. But the voltages that it can provide are limited by the voltages which are the voltage range which is provided to the operational amplifier. So it can't output more voltage than it's being given, which should make a certain amount of sense. So, conceptually, if you, this is a vast simplification of the guts of an operational amplifier, but, it's so good for our purposes. This resistor here is a high impedance resistor. The idea is that we have this impedance so high that we can ignore the idea that there's any current flowing through this resistor at all. So these resistors, the resistance across those two terminals is normally better than 1 mega ohm, right? Which if you take two sides of a voltmeter, and anybody done that? Measure your own resistance. How many people haven't measured their own resistance? Oh, come on, you have to sometime. It's fun. Anyway, a human being's resistance, depending on how much water they drink, I guess, it'll probably come in at a couple of mega ohms, but it depends on how, it depends on your equipment. But anyway, So we've got the input impedance very, very high. We've got the output impedance, which is this resistor here, which is reasonably low, say less than 100 ohms. In addition to that, we model these guys as having a voltage source embedded here. So, you can probably be pretty well assured that somebody has done a Thevenin equivalency on this circuit for your benefit, so you don't have to worry about it, at any rate. We have a non-inverting and an inverting lead. In general, there's that's more of a convention thing than necessarily something that, affects, At any rate, you have a voltage applied to the plus, you have a voltage applied to the minus, the non-inverting and inverting inputs, right? Your output voltage here is K, which is a gain factor. K is often what's used for gain, which is whether you're amplifying a signal or attenuating a signal, K is some constant number you are multiplying by another thing to get the output thing, right? So the input, Vin, is the voltage across these two leads. Vout is K times Vi, right? Now K, for these guys, is very large. 10,000 to a billion, right? That's a huge range, right? So, of what possible good is this, right? Well, the members only section of the lecture where only subscribers get to see what goes on here.
Patreon for more?
No, I don't want to be beholden to a bunch of crazy people on the internet. So that's no Patreon. Anyway, and I'm already being recompensed by the university. So anyway, so operational amplifiers. You have a zone inside which the output is linearly related to the input according to the gain factor. This is very, very small if you consider how large K is. Most of the time, you will be in the saturation zone, right? Which is the zone where we've hit the positive and negative voltages which are being supplied to the operational amplifier, right? So, saturation. Good. So, before we, okay, I know I'm jumping around. I'm deciding which order I want to attack this in. So before we begin our analysis of operational amplifiers, we must have two very, very important principles which are derived from the ideal op-amp, right? So no op-amp is actually ideal, but these two properties are held most of the time. Don't ask me why or what the circuitry is that ensures these things are true, but, it would be very complicated. But these are the two things that you require in order to do any op-amp analysis, which, may very well be in your future. Just saying. Hint, hint. So, number one, you must consider the voltage at the input leads to be equal, to be held equal, right? Think of the amplifier itself as working in order to make sure that V plus is equal to V minus, right? I know that doesn't make sense on this diagram, but normally we put resistors and stuff in the way which results in that actually being the case, right? So, this voltage is equal to that voltage. Rule number 2, no current passes into the input lead. So I going in is 0, right? So, with these two principles, we can do some fun things. They're like, I don't know if it actually sounds like fun. And I'm like, shush, this is my class, I say. Anyway, so just before we get into the analysis, the stability of these op-amps, so this K value can vary quite widely. It's due to a number of reasons. The gain can actually drift as it's being powered on. It's caused by a number of things. It can be temperature, humidity, age, all kinds of factors can affect K. You can't really rely on the gain being any particular gain, right? So it's assumed to be frequency independent in a range that's less than 10 kilohertz, which, you know, is not true in general, but, you know, relatively true. So they are subject to some frequency problems. These things actually are a main component of active filtering. If you build a filter and you want like decently steep drop-offs inside of at the end of your bandwidth, then you would want an active filter, and operational amplifiers are the main component of most active filters, as we're going to see later on. So, we can use feedback to mitigate the effects of op-amp stability. Passive elements, such as resistors, capacitors, etc., are used in practical applications in order to impose a particular gain. So, this is the simplest feedback configuration for an operational amplifier. This is known as a unity amplifier. It amplifies with a K equal to 1. So all it's doing, again, taking some input voltage, which may have a very high impedance, and outputting it in such a manner that it could be actually read by something, because the slew rate isn't terrible. Unity amplifier. So, things to note. Number 1, V in is equal to V plus. V plus is equal to V minus. There's no resistance here, so there's no voltage drop here. So V out is also equal to V in. Make sense? Sort of? I'm getting some blank stares. Yeah? All right. So that's basically how it works. So we can affect what this, we can make it so that K is some value other than 1 by introducing some resistors, right? Which I'm not sure we're going to have time for the whole thing. But here is your typical voltage amplifier. So we've got the inverting lead is connected to a resistor and then connected to ground, right? Before the resistor, we have another resistor which is connected to the output of the operational amplifier. The voltage here will be considered V out, right? V in would be right here. number one, let's describe some currents. I'm just going to assume that that's fine like that. So, I1, I2, this guy right here will be I3, I4, I5, I6. Right? We can assume that this is connected to some load, you know. So, number one. These two voltages are the same, right? So I'm just going to call them, I'm going to call this point A, and this will just be V in, right? So, VA is equal to V in. Op-amp law, right? Number two, let's start assigning some equations to these currents, right? So we know I1 is equal to 0. We know that's also equal to I3, op-amp law, right? We know that I4 is equal to I2 plus I3. So we know that I4 is equal to I2, right? We know that I5 is equal to I4 plus I6, right? Good. So now, we can actually determine what these currents are using Ohm's law. So, first, I2 is equal to VA over R, right? Voltage, VA, 0, voltage drop is VA, so that's I2 is VA over R, right? So, we therefore also know that since there's no resistor here, Vout minus VA is equal to I4 times RF. RF. This is RF. This is R. Right? So, VO minus VA is equal to VA RF over R, right? Of course, we also know that VA is equal to VI, which is the input, so we can just rewrite that out like that. So, VO is equal to VI RF over R plus VI. Collect the VI, right? The output over the input is 1 plus RF over R. So, if you want to, and this output over input is generally speaking how you describe, like you'll see it in 3DX4 when you guys take that next year. This is an equation which relates the output, and like it's the factor by which the output is scaled with respect to the input. Anyway, so equals K. So by modifying the values here, you can get whatever gain you want, right? If I made RF into 40 kiloohms and R into 20 kiloohms, I would get 1 plus 2, which is a gain factor of 3. Right? So that's how you amplify signals. Make sense? Good. Any questions? Yes.
Which one's RF? I can't really read it from over here.
This one.
Okay.
Yeah, sorry, it's... I'll do it in the middle next time. Okay?
Alright.
All right, in that case, thank you very much for your time and attention. See you next week.